Good morning, dear students. I am Dr. Likha Chandran, working as an assistant professor teaching chemistry in the Department of Science and Humanities from MLR Institute of Technology, Hyderabad. I would like to talk with you regarding engineering chemistry, particularly emphasizing the focus on polymers. We all knew that all plastic are polymers, but all polymers are never plastics. The class for today will be having an introduction, then what are the different characteristics of a polymer, and how the polymers can be mainly classified. So, what do you mean by polymer? Polymer is a Greek word which means poly meaning many and mer meaning repeating units. That means many repeated units linked together in a chain form to give a long macromolecule which is known as polymer. So, we can define as polymers are the macromolecules formed by joining of repeating structural units on a large scale, and the molecular weight of these materials will be in thousands and thousands. And each repeating units, right, we have like many repeating units now. In that, each repeating units or each repeating structures are known as monomers, or the smallest building block of a polymer is known as monomer. In a schematic diagram or a diagramic way, we can represent that as like this: a chain which will be linked with each another molecule and forming into a long chain. Each of them will be having same properties, and one of this is known as monomer. This completely will be known as polymer. Now, so we can say that clear definition of polymers are like long chain macromolecules made by small repeating units known as monomers, and the monomeric units contained in a polymer chain is known as degree of polymerization. So, what do you mean by degree of polymerization now? The number of monomeric units contained in a polymeric chain. That is, if there are n numbers, like if we are writing C, this is a chain, right? All this, how many numbers are there? That is known as degree of polymerization. So, how can we define degree of polymerization? Degree of polymerization is molecular weight of total polymer chain divided by the molecular weight of one monomer. That is, what is the molecular weight of all these things, isn't it? Combined with 1. So, if we can write CH2 like polyethylene, simple example, CH2 double bond CH2, we can write the polymeric as C N. The whole weight of this, that is molecular weight of a polymer divided by the one monomer, because it is getting repeated, isn't it? So, one monomer, so total weight divided by one weight is known as degree of polymerization, and it will be always represented by the term N, because we don't know what N is or how much it will be. Since it is a long chain macromolecule, it is indefinite. We cannot define it anywhere. It is like indefinite monomeric chain or macromolecular chain. So, degree of polymerization is, in simple terms, we can say that molecular weight of the polymer divided by molecular weight of the monomer. So, when it is like higher degree of polymerization, when the polymers are having higher degree of polymerization, it is known as high polymers. For example, when the molecular weight of a polymer is around 75,000, then it will be known as high polymers. And whereas when it is having a low degree of polymerization, or then like in the range of 10,000, 10K to 15K, that will be known as oligopolymers. So, high polymers means when the degree of polymerization is very high, that is the molecular weight of the polymer is 75, like above 50,000. And when the oligopolymers or low polymers is that when the degree of polymerization is low, it will be in the range of thousands, like 5,000 to 15,000 or 20,000, in that range. So, degree of polymerization is, in simple terms, we can say that molecular weight of a polymer, that is in simpler terms. We can simply say the example of polyethylene, which I showed earlier, CH2 double bond CH2. What is happening with CH2 double bond? When it is undergoing polymerization, this double bond is splitting into single bond, and it is like moving both sides, like delocalization of pi bond is happening. This separation or moving is known as delocalization of the bonds. So when delocalization is having, another molecule of carbon will be attached. So this chain, again it will be having a double bond which will be again shifting. So this will be continuously working on or moving on, and we can say that it will be forming a CH2 double bond or single bond CH2. This will be continuously moving, and it can be represented as an N number of moles or by the term N, which is known as, this is known as degree of polymerization or the molecular weight. Whatever number we are writing for this is defines the molecular weight of that particular polymer, or defines the degree of polymerization of that particular polymer. In one more terms, we can say for this is functionality. Now, what is functionality? Functionality is nothing but reactive sites of a monomer to make into polymer. That is what is known as functionality. For example, here in this polyethylene, we can say that double bond is there, isn't it? So, this double bond is the reactive site because all the attacks are happening in this bond here. It will be shifting. This pi bond will be shifting. In some material, we can say that OH will be there. That is functional group. Here the attack happens. Some it will be like Cl. Then Cl is the functional site. So, where the groups, functional groups are present or arrange it as an active site for the polymerization to take place, that is known as functionality. So, when a polymer is having one functional group, it is said to be like less stable polymer. When it is having two or more active sites or functional groups present, then it is known as highly stable or a good polymer. That is how polymers will be. When there is no functionality, still a polymerization is happening. That takes a lot of energy or emits lot of radiations. That is known as a weak or unstable polymers. So, weak polymers are when only one polymeric site or one reactive site is happening, and when it is having two or more active sites or functional groups present in a monomer, then it is known as high or stable polymers with good functionality. Now, for each and everything around us, we have different characteristics, isn't it? So, like that, what are the different characteristics present for the polymers? We can say that polymer should be of low density. Why low density? Then only the attack of monomers is very easy, so that we can write as this continuous chain formation will be easy only when the density is low. For example, we can say like one person with a very thick or thin, two different persons, a fat guy and a thin guy. How it will happen? A thin guy can join many people together, isn't it? A fat guy will be taking more space to be joined. So, what happens? In that case, when the density is less, okay, that takes or the density is less, then the polymer will be a good polymer. So, the polymer should have less density. Then it should have low coefficient of friction. Why low coefficient of friction? Because friction is the place where friction is where between the sliding parts or moving parts, right? We have to reduce the friction so that it can have better works, it will be efficient. So, when the polymers has to be used as a sealant or used as a reducing agent for frictions, it should have the friction coefficient should be very low. Then good corrosion resistance. Yeah, good corrosion resistance means this polymers comes into application in many parts, in many areas like automobiles, medicine, then in daily life, everywhere. So, and it will be attacked to all the environmental conditions like sunlight, temperature, climate change, water, like vapors, everything. So, if it is getting corroded soon, then we may have to change it repeatedly, which is not good for a material. So, good corrosion. So, it should be like it should not get corroded very fast. In that way, it should be maintained. Then comes poor mechanical strength, obviously, because low density is there, isn't it? So, when low density is there, the mechanical strength will be poor. When take the same example, a guy is little bit fat and the other one is little bit thin. What happens when the guy is fat? It will be having a good strength. Not always, but still. But a guy who is little bit thin, what will happen? The mechanical strength will be very less, isn't it? So same thing, when the guy is having, or when the material is having low density, mechanical strength will be less. It can be easily prone to attacks, but when it is having high density, the mechanical strength will be low. But since polymers, since it has to form a macromolecular chain, the density must be low, so obviously the mechanical strength will be less. And poor tensile strength. So again interlinking, poor mechanical strength, when it is having poor mechanical strength, it can break very easily, isn't it? So when it is having poor mechanical strength, it will be having a breakable property. Tensility is nothing but it up to at a limited temperature or a limited time, how it maintains its original thing, and when after that it starts breaking. So it is like tensility is that breaking. So mechanical strength is less, then the tensile strength will be less. Poor temperature resistance, yeah. Since low density, mechanical strength is less, tensile strength is less. Now what happens? So we cannot take it into more higher temperatures. It will be having a limited amount of temperatures. It can withstand up to a limited temperatures only, because more means it will start breaking very soon. Since mechanical strength and tensile strength is less, so higher temperature if we give, it will start breaking very soon. So it will be having a poor temperature. Above all, it is highly cost effective. We can even make the polymers from our daily life materials itself. So it is highly cost effective. So different characteristics of polymers, we can again tell that it must be low density, it must have a low coefficient of friction, then it should have high corrosion resistance, poor mechanical, it will be having a poor mechanical strength. Because of poor mechanical strength, it will be having poor tensile strength, and it is having the nature of breaking down very fast. Then it will be having poor temperature resistance, that is, it cannot withstand up to a higher temperature because it will break soon. And above all, it is highly cost effective. Now, we characterize the different types of polymers, isn't it? We can classify or characterize polymers on basis of their properties. How will you now classify the polymers? What are the different ways to classify? For a human, we can classify at the height, weight, color. Yes, isn't it? So all these different things will be there to classify a particular human. So in the same way, a polymer, how it can be classified? There are different ways how it is classified. So first one is based on the source. Classification based on the source. Now what does source means? From where it is origined. Origin. So in that case, classification based on origin also we can write, like source or origin. In that case, it can be classified into two different types, that are natural and synthetic. Now what is natural? That is, which is naturally available. Example is rubber, isn't it? Which is very naturally available, natural rubber. So that is natural. Then comes starch, cotton. Cotton we knew it will be there in many farms or in our home itself. Starch. Starch is like carbohydrate, like we can get from many vegetables. Tapioca, then comes from the potato. Wherever the carbohydrate content is high, there will be get the starch. So when it is having a naturally occurring, or when it present in the nature itself, it is known as natural, and when it is like man-made from the nature, natural polymers. From the protein, if it is made, then it is known as synthetic, and all these things are from the natural sources itself. This example is, I gave this because this is a wrapper, toffee wrapper, which means that it is from this toffee wrapper is made from cellulose. Component is cellulose acetate. This is like, and this rope, daily life we are using, isn't it? Nylon, which is from the adipic acid. So again, that is present in the nature. Next comes the classification based on structure. How a polymer can be classified based on the structure. Based on structure, it can be classified into three different types. First is linear polymers, that is continuously a long chain polymer will be formed. We can n numbers, C. Why I am particularly writing C is because all the polymers will be basically based on the hydrocarbons. So it will be continuous, a long chain polymers will be happening. This is how it will be. Okay. That is high density polyethylene, that the density is very high, or polyvinyl chloride, PVC. Polyvinyl chloride, what is vinyl group now? CH2, double bond CH. What happens with an X? Anything, any halogen, that is known as vinyl group. So if in terms of X, if it is Cl, then it is polyvinyl vinyl chloride. This is known as vinyl chloride. So when it is polymerized, we can get as polyvinyl chloride. So all these are very strong, isn't it? PVC is very strong. Polyethylene, polyethylene means nowadays what covers, plastic covers which we are using, no, that is polyethylene. It is very hard to break, like compared to the previous types, it is very hard to break. So that is known as high density polyethylene. So this is like then structure, how it will be, long chain, it will be a continuous chain going on. Second type is the branched chain, chains with branches, right? From the name itself it is clear, and it is like low density polyethylene. Example, like how it can be represented as C, one branch it will be happening here, C, again it will be moving another branch. So this way it will be having a branched structure which can be, it's like always the polymer should be denoted in terms of N, okay. So it will be like in this way, continuously it will be chained but along with the branches, that is known as branched chain polymers. And the example is low density polyethylene. We wrote that C, right, carbon, same thing. Now it is like CH2 here, this will also be CH, C, CH2, like that, it will be moving like this, okay. So this is known as low density polyethylene. This is easy to break because it is having a branches, isn't it? It is like unstable here, it will be like hanging up, it will be unstable, so anything from the outside can break over this. So it is easy to break, that is why it is low density polyethylene. Earlier times this was there in the markets, commercial availability, low density polyethylene. So this was now completely removed and made into high density polyethylene, so that it is not breaking soon or faster when compared with the low density polyethylene. Now comes the third classification, which is known as cross-linked or network polymers. Now what is cross-linked or network polymers? That is, it will be having like, instead of C I am taking like two different monomers A and B, okay. Now what happens with A and B? It will be completely moving, A, isn't it? Then B comes, again from B, A, like that it will be completely cross-linked. For in order to understand in a simple terms, we can say that making of wall, normal wall which we are having, no, how it will be having a different bricks layered in different ways, right? So each layer it is like cross-linked, it is not in an arranged one will be there, the gap other bricks will be there, in that way it will be cross-linked. So best example is bakelite. Now here what is happening, continuous everywhere it is forming, isn't it? So stability will be very high for this material, okay. The stability will be very high, it is like unbreakable, it is very difficult to break. It's not like unbreakable, it is very difficult to break when compared with the branched and linear chains. So this is known as, like one such example is bakelite. Bakelite is daily life, we can see bakelite application in the switchboards or like in the plug boards, switchboards and all, no, that material is bakelite, it is difficult to break. So all these are the basis classification based on structure, like linear polymers, branched chain and cross-linked or network polymers. This is how the cross-linked or network polymers will be. It will be having a cross-linking which that the attack from the outside is difficult, so that it will be very strong. This bonding will be very strong that it cannot be broken also. In the sideways it can be attacking, fine, here also it happens, but this bond cannot be broken. So that what happens, it's very strong that it can withstand up to higher temperatures also, and it can be used in many applications where the strength is to be needed. Now classification based on intermolecular forces of attraction. Now what is intermolecular forces of attraction? For that we can say that the molecular forces of attraction between two different atoms or two different molecules. Now for simple example I can write as water. What is water? It will be like H, this bonding, two different, okay, or this bonding. This is known as intermolecular forces of attraction, which according to this how the polymers will be classified. So it can be classified as elastomers, then it as fibers, then it can be given as a plastic. In plastic it can be two types, thermoplastic and thermosettings. Now what is elastomers? Elastomers means when the bonding between two molecules is like very weak, okay, that is known as elastomers. It will be having an elastic nature, it can elongate but it cannot break or turns, that is known as elastomers. Now fibers means which will have a strong intermolecular force of attraction, so that it can use into the applications of textiles mainly, okay, that is fibers. Now comes the plastic. Plastic can be plastic we know that it can be molded also, it cannot be molded also. So those plastic which can be remolded by heating and cooling, they are known as thermoplastic, and which cannot be reused or remolded, that are known as thermosettings. So for example, polyvinyl chloride, say like PVC. PVC is like when we heat, it will change its shape and it can be formed into different shape. That is peculiarity of PVC, isn't it? So it can be like in that way, thermoplastic. And in case of thermosetting, it cannot be, once a shape is defined, it cannot be molded by any terms of heat or light. That is simple example we can say is bakelite. Now comes classification, which is based on the mode of polymerization. What is polymerization? The way it is formed or reacted. It can be of two types. That is, one is by the addition polymerization and the other one by the condensation polymerization. Now what is addition polymerization? In simple terms, when two monomers are getting added up, continuously getting added up without the elimination of any small byproducts also, that is known as addition polymerization. Self addition of several monomers, that is known as addition polymerization. The best example we can say is again polyethylene. It is getting added up, right? CH2, double bond CH2, it is continuously added up. It is not giving any residues out. So this is known as addition polymerization. Now comes condensation polymerization. So it will be just opposite of addition polymerization, isn't it? So what is now happening in this? Addition will be happening, but with an elimination of a small or simple molecule like water or carbon dioxide or ammonia. Anything will be liberated out. We can see the formation of nylon 6,6. What is in nylon 6,6? Hexamethylene diamine with adipic acid. Hexamethylene means CH2 will be of 6 times and a diamine NH2. This is diamine. So hexamethylene diamine along with adipic acid COOH, which is CH2 4 times, right? So what happens here is this H2O, isn't it? It is getting condensed, completely joining together and removing off, eliminating off. The rest everything we can see that it is rewritten. Yes, again this H will be again joining with this OH outside. Any other molecule will be there? No, it will be continuous chain, right? So it will be just, so all this like H2O will be eliminated and rest everything will be condensed together or added together to get a new polymer. This is known as condensation polymerization. So how can we compare or distinguish between addition and polymerization? Addition polymerization, it should have, a monomer should have a double bond or a triple bond, but in condensation, two dissimilar or two similar functional grouped material can be used or you work as a monomer. In addition, there is no byproducts, but in condensation there will be a small amount of byproduct in like HCl, water, ammonia, anything. So in addition polymerization, the addition of monomers result in the formation of the polymer, but in condensation, condensation happens between the formation of polymer. Then in addition polymerization, molecular weight is like multiplied, it increases, but in condensation it is not multiplied, but a less small amount of it is getting reduced. In addition polymerization, we can say that we need an initiator or a startups, okay, which can give the energy to get it added up. Okay, a small amount of catalyst or initiator is needed. But for condensation polymerization, there is nothing like that. We can, like different molecules, if it like unstable, they will be combining together to form a stable condensed polymer. So simple example of addition polymerization, we can see that PVC, polyethylene, PE, anything. For condensation, as we told, like bakelite, nylon, everything. So I hope today's class you might have learned at least the basics of polymers. And like what is polymers we learned, then comes its characteristics, then we looked into classification and different types of classification. All these were today's class. For the next time we will be doing how the classification from the addition polymerization, what are the different mechanisms of addition polymerization and how a monomer is converted into a polymer with the help of a free radical mechanisms. Thank you.